Oh, okay. Welcome to EE483, the summer session. My name is Satorius, Edgar Satorius, and I am the instructor. Here, I'll put this up here. I am the instructor for the summer. So welcome aboard. As I sent out an email, so if you can get on to Den on the blackboard, make sure that you look at the announcement. As I pointed out in the announcement, this first class, which will be shown or observed May 21st, I will actually be out of town on May 21st. And so that's why this first lecture is pre-taped. But I'll be there for the rest, so make sure you all come back. You're all come back after the 21st, the 28th, and so on. I will be back in studio for live classes. So this is the EE483, Introduction to Digital Signal Processing. The class meets 6:30 to 9:10 every Wednesday evening. I always have a break around, somewhere around 8 for 15 minutes or so that you don't have to sit there for the full 3 hours or 2.5 hours. And it will be in OHE 100D. And it ends on August 6, 2014. August 6th is the last day of class, but it will also be the day of the final. So if you're wondering about the final exam date, that will be the last class, August 6th. And I'm guessing it'll probably, depending on the number of students, probably be in our classroom, but we'll see. Right now, as of this point, since this is still sort of early, this is the date I'm pre-taping this is actually May 9th, so it's almost 2 full weeks before the actual first class. So at this point, there is no TA or grader that's been assigned. We're kind of waiting to see what the enrollment will be. So again, I encourage you all to enroll and have 100 people in the class would be great. Well, maybe not 100. Here are some important dates for you. The midterm exam, that's going to be June 25th. That's about the 6th class in that I usually find to be a convenient time to cover, basically the first part of the course. And then the final, which will cover only the second part of the course, will again be August 6th. And these are hard dates, so make sure that you have no conflicts with these dates. So what this course is about is to provide you a basic introduction to the theory of digital signal processing, or DSP. Now, I'm aware that some of you probably have had some background courses, or the only real requirement for this, or prerequisite, I think, is the linear systems course. But I'm now digital signal processing is so pervasive that along with the tools like Matlab, that I would be not surprised that a fair amount of you have had some exposure and some use of digital signal processing. But in this class, I'll teach you the background, pretty much the theory behind digital signal processing. And I think more importantly, I shouldn't say that, but as important, we will have some projects that will further teach you the basic ideas of DSP. The projects where you can actually do a MATLAB type analysis, simulations. And I've talked to students in the past in 483, and believe me, they learn a lot from these projects. So, and I try to have projects. I myself work at the Jet Propulsion Lab, so I I've worked in industry for years, so I have a lot of experience with applications of DSP in industry, so I've kind of tailored, I like to tailor the projects toward that. So I think you'll find them quite interesting, useful, and instructive. So I think that plus the theory, as I said, even if you've had some exposure, more or less, to DSP, I think you'll still find this very, very useful in your work. And so what we're going to study on the theory side are things like filter design, linear digital filter design, both what we call finite impulse response filters. Those are filters with, as the name suggests, impulse responses that are finite length, and these are all digital filters, as well as infinite impulse response filters, or IIR filters. And you will see that the structure of the IIR filters can be conveniently expressed in a block diagram form. And so we will talk about that. We'll talk about block diagrams. Like I said, get into some of the implementation issues. We will also study the discrete Fourier transform, or I call it the discrete time Fourier transform, and its properties, as well as to get you kind of familiar with the terminology. So there's two types of Fourier transform, digital or discrete Fourier transforms we'll talk about. One is the discrete time Fourier transform, that's called DTFT, and the other is the discrete Fourier transform, or the DFT. So there's both DTFT and DFT, and these are actually different transforms. You would think the inclusion of T into the acronym wouldn't change much, you know, of the transform itself, but it's totally different. And so we'll talk about that, learn how to use those transforms, because the DFT can be implemented with something called the FFT, or fast Fourier transform. So we'll go through all that. We'll also discuss sampling and the sampling theorem and the relationship between the continuous and discrete time transforms. And also, we will talk about something else called multi-rate DSP. So that's used a lot in actual applications of DSP and implementations of DSP. So I think you'll find that to be very useful and interesting. And then we will talk about linear shift-invariant systems, how they're characterized in terms of block diagrams and linear difference equations, talk about that, and the impulse responsive filters, and also something called a Z-transform. Now, I ask many times people that have had exposure to DSP and have had linear systems, most of them have heard about or know some knowledge of discrete Fourier transforms, or at least discrete time Fourier transforms, but not as much about the Z-transform. And the Z-transform plays an important role in digital signal processing, as we will see. And after we've covered all that, then we will actually discuss some actual filters and implementations, and then ultimately we'll end up with, and some additional topics, design and implementation of digital filters, and I'll also talk about some topical material, like what is bandpass sampling, what are polyphase filters and polyphase filter banks, and possibly talk a little bit about adaptive filters, and then we'll end the class with digital filter design. So I think you'll find the class very interesting, and I think and I hope you find the projects enlightening for you. So that kind of gives you an overview of the material. I have, by the way, this is the syllabus. This has already been posted both at the USC site and on the Blackboard. So if you haven't got the and also on the Blackboard, I have posted a couple of course notes, one of which I'll certainly cover tonight, and probably a little bit of the second one. So what I suggest is you go to the Blackboard, the DEN Blackboard site, and you look under course material or course content, I think, and you'll find all of the lecture notes that I post, you will also find that there's a date on those lecture notes, or any postings will have a date, whether it's assignment or lecture notes, so that, you know, you can see, oh, okay, well, this was posted on such and such a date, and therefore I know I already have that. So that's a way for you to catch anything new that I posted that you didn't see. So go to the site. There's only 2 lecture notes right now that have been posted, but go there and download those, and that way you can follow the lectures notes. And in terms of downloading, I mean, you can follow the whole thing on your laptop, or, you know, nobody prints these notes out anymore. When I taught this a long time ago, we used to, you know, everybody would print out the notes, but now everything's on the laptop. So however you do it, make sure you download the notes. Also, I have included in the syllabus the required text notes. Pretty much there's just one text. That's text by Mitra called Digital Signal Processing, a Computer-Based Approach. If you have the 3rd edition, fine. If you have the 4th edition, that's fine. I have a copy of the 4th edition, and I think 3rd too. So some differences in the editions. I notice that primarily certain chapters are enhanced or taken out in favor of other chapters, and so on. Clearly, just so you don't panic, I mean, we're not going to... This book is over almost 1,000 pages. Now, we're not going to cover every single page in this book. So we're going to kind of skip through the book. We'll focus on certain areas, less on others. And the areas we'll focus on are pretty much what I said a few minutes ago, namely the DFT, the DTFT, Z-transforms, etc. So that will be covered in the book, and some of the homework problems will be from the book too. So whatever edition you have, 3rd or 4th, or even an earlier one, make sure you have that book to follow. Now, if I assign homework problems out of the 4th edition, which I will, all the homework problems will be out of the 4th edition. I'll make sure that I either, you know, print those out so people with an earlier edition will know what the problem is. So that's our course text. There's also, under required text, the student edition of Matlab. Nowadays, you know, everybody, so many people know Matlab that you don't really need this reference. So I will call that optional. If you need it or want it, I made that available at the bookstore. And then the supplementary class notes. Those are the ones I just mentioned. I posted 2 already on the Blackboard. Keep checking the Blackboard for new postings. Probably the 2 will remain there until the class starts actually on May 21st. But anyway, again, I encourage you to download those. Access to all the DEN website, as you know, probably by now, requires login with an individual ID and password. And if you can't get on or anything, contact the DEN folks. But I'm sure that by now most of you have used that site. I also have some recommended reading. You know, the Shams outline is always a good source. They have a lot of problems. But I should encourage you, make sure you, or, well, I should say, if you have problems, you can, this is a really good reference. In fact, this is the Discrete Time Signal Processing reference by Oppenheim and Shaffer. And this is classic, and actually it's a model for most of the other introductory texts. And I would highly recommend it as a reference. You know, most of the material in this, of course, is in the Mitra course text, but this is a very, very, very good reference. And, you know, then these are some other background references, more if you're practicing DSP or using it or studying it further. These are good recommended reading texts. Okay, so let me end, or not end, but geez, don't get excited. Let me continue with the syllabus. Here's a topic that everybody's usually interested in. How do I establish grades for the class? Well, I base it on 3 components. One is the midterm, and they all count roughly the same, or actually 4 components. The midterm, which, as I said, is, what did I say, June 25th. I don't know, maybe, did I say June 26th? Well, anyway, it should be June 25th. So that's the midterm. The final, of course, that's also 30%. And then the 2 Matlab projects, those are 15% each for 30%. So that's 90, that leaves 10, and the 10 is covered by the homework. So, and I will typically sign, it's not really stressing regarding the homework. I mean, it's not like you don't get one every class or every other class. Well, I'm sorry, no, let me restate that. You don't get like 2 homeworks a week or 1 homework. Typically, there will be a couple of week break between homework sets, and we may end up with 5 to 6 homeworks. I probably, I may post one. In fact, maybe I will post the first homework set before you, or rather before I go out of town, just so you have them. But in any case, those are the homework. 2 MATLAB computer projects, and these, the homework sets will, I can read this, will help prepare you for the midterm and final exams. The MATLAB projects will help you learn the material by conducting practical computer experiments on real-world problems. So I stress that. Both of those are very important. So, you know, you might say, well, geez, homework's only 10%. Let's say I don't even turn in one. That's only 2% of my grade. You know, well, obviously that's your option, but I encourage you to do the homeworks because they will help you prepare for the exams. You can certainly talk about the homework problems with your friends. We've always had this, or groups, if you want. I've always done this in the class. But the homeworks, the write-up, the stuff, that I want you to do on your own. Likewise for the Matlab assignments. Again, many students will discuss those with other groups, maybe in a study team or whatever, but again, you have to write up the Matlab assignments by yourself. Both of the exams, midterm and final, will be closed book. So I don't know, sometimes you take a class and they have homework assignments and you faithfully do the homework assignments, and then the exams are totally different. So, but in this class, no, if you can do the homework assignments, they will help you for the exam. So please, I encourage you to do that. I've had this, now here's a policy on late assignment submittals, and I've had this policy for years, and it does lead to some I don't know what to call it, a little bit of difficulties at times, but more for me and the grader, but or the TA, whoever it will be. But I'm going to keep this policy, even though most classes say, look, you know, you have a homework assignment. If that's not turned in by 5 o'clock the day it's due, it won't be graded. Well, you know, there's some advantages to doing that. I mean, you get what you get. But with me, I'm going to stick to my policy on the late submittals. But I am going to stress something. So I will allow them. I will allow late submittals on both the projects and the homeworks. So you might think, geez, you know, I could really do that homework, but I don't have time. I have another exam. I have another big project. If I could just have a weekend to finish it, I know I could really do it, and I would get credit for that. You can do that. But here's what you got to do, and I'm going to really stress this or enforce this. Provided, here's the caveat, you have to let me know in advance via email. So if the homework is due, the homework will be due Wednesdays. Obviously, that's the class, and you realize Thursday, oh gee, I need to send the professor. All you have to do is send me an email, but I need to see it before the homeworks are due. So if the homeworks are due at 5, you send an email that day before the class. Fine, that's fine, but you have to send me that email. And also, when you do send the email and ask me, hey, is it okay, Professor, I'm going to submit my homework late, also, which people haven't done in the past, when are you going to submit it? Hey, professor, I need 2 more days. I need 3 more days. Okay, so that's all I ask. But if you do that, then you can submit the homeworks or the projects late under that condition. Now, the other caveat is I typically post solutions about a week after the assignments are due. Also, there's another thing too. Before the midterms, if I have a homework due the week before that, I will even post solutions earlier so that students can study the solutions for the midterm or for the final. But generally, I post the solutions about a week after the assignments are due. So that kind of gives you a window. I will not, now I can't accept any solutions, any homeworks after the solutions are posted. So you typically have about a week window that you can ask for late time. But I need you to let me know before the homework is due. And again, when can you get it in? How many days do you need? Up to the week time period. One other important note regarding assignment submittals. Oh yeah, well, this was something that happened quite a while ago in another class that I taught. So, but I'll say just all I ask is that you not interrupt the class to submit your assignment. I taught a class many years ago, and the student would come in right while I was lecturing, stop, hand me his homework, and take off because he wasn't attending the class. I guess he was watching on video. So don't do that. You have to submit your assignment either before or after class or during the break. So if, for instance, you want to watch me on streaming on the streaming video on the video link, and you don't want to attend the class, fine. And if you're on campus, then bring the homework assignment in before the class and or during the break. And the same general rules apply for off-campus students. Now, as of May 9th, the date of this, there are more off-campus than there are on-campus students. We'll see how that goes. But for off-campus students, a little bit easier. You don't have to submit it in person. You can submit it, you'll submit it through DEN. Now, one other thing, here's another option. If you submit the assignment late, if you say, okay, professor, I need 2 more days, another option for on-campus students, I usually can collect the assignments after the class, okay, or, I gather all the assignments and I put it in a waiting box for the grader or TA. But if you're on campus and you want to, on-campus students, I should say, you can submit electronically to me. Submit to me or the grader. Okay, so that's another option you have. That means, of course, you have to scan your homework set and submit it. But you can do that. I do that a lot. I've used that a lot. It's a little bit cleaner. You don't have to worry about hard copies during the class. But if you're going to submit your homework, if you haven't sent me a notice saying I need a late homework, then you have to submit those electronically. As soon as the class is over. If you haven't sent me an email and said, hey, I need a couple of more days, then I'm assuming you're submitting it on time, and that means that it has to be submitted electronically. I will give you till the end of the class. So that's another option by class end. Okay, so you could do that too. Or hard copies. Hard copies are fine, but if you submit hard copies, they have to be submitted during the class period when the homeworks are due. Like I said, typically 2 weeks after they're assigned. Sometimes it might be a week, but normally 2 weeks. Okay, so here's the deal with my office hours. They are 5 to 6:15. I'll try to be there at 5, and they are in Pal Hall 414. And or if you want to call that office, there's the number to call, or you can arrange a separate appointment. I'll leave that up to you. But I strongly encourage you, and that's a good time to talk to me about problems or anything else you want to talk about. That's fine. Of course, priority is always given to students with specific questions about problems that I've been assigned, or any other thing related to the course. But yeah, if you want to just swing by some afternoon and talk to me about problems or DSP in general, that's fine. But here's another one. I encourage you, underline this. This is my email. That's a good way to go too. We can nowadays with email, you can scan notes and stuff in. And I find that to be very, very useful and simple because I don't need to be there, and we can cover. So any questions, almost any questions on homework you could ask during office hours, you could probably send those in via email. So I strongly encourage you to do that. And my policy is I get back to you within a day on email or sooner. And you can ask other students who've taken my classes. And I always get back, and I will respond. Generally, I respond personally unless you've sent the email to the TA or the grader. So that's kind of the deal on that. So again, I don't know the graders or TA haven't been assigned, so we'll see what happens here. Here is the basic topics. I've talked about most of these. And by the way, I don't have it here, but I've indicated the sections in Mitra. So these are some of the topics I want to cover, and I've indicated what sections of Mitra they are in, but I'm trying to see something here. This is edition 4. Let me see. 2.1 through 2.7. Wait a minute. I will know. Frequency main. Z transform. 6 sections. All right. I'm thinking these are certainly edition 4. Okay. So anyways, I've mentioned the general topics we're going to cover. Specifically, introduction to discrete linear systems. Talk about that. Probably finish that tonight. Discrete time Fourier, that's the DTFT I mentioned. There are the sections in Mitra, so you can tell by the way, looking at the Mitras that we're jumping around in the text, not covering every page. Then we will spend some time on the Z transform. I also try to indicate how many class periods each one. The introduction to discrete time linear, so I could probably finish that tonight. I don't have a lot of material on just the basic definitions. The DTFT and linear time invariant systems probably a little bit tonight in next class, the Z transform next class, and in the third class, etc. And then we're going to talk about properties of digital filters. That's first time you get a chance to actually see some practical filter designs that we will be looking at. And those are all different types of filters, from very simple averaging filters, which, by the way, are FIR, finite impulse response. Recursive averaging filters, that's an infinite impulse response. To notch filters, all-pass filters, those are very interesting. Comb filters, equalization, etc. And then we're also going to talk about something called group delay, linear phase, all-pass, minimum phase. So that'll be some theoretical discussion, all to help you out learn about filters. And then at that point, we're ready to start discussing Fourier transforms and sampling. And that's probably going to cover most of the rest of the classes up to the midterm. And then the midterm, as I indicate, will be June 25th. That will be the entire class. I won't attempt to have a separate lecture or anything like that. It'll just be the whole class, probably a couple of hours, closed book. So write that. So please write that date down. It's very important. And then the second part of the class from there on will be Fourier transforms, sampling, all different types of things about sampling, and some practical aspects of A to D converters, etc., depending on how much time we have. Then the DFT follows next, and maybe I will discuss a little bit an implementation of the DFT called the FFT, the fast Fourier transform, digital filter design, and that will about cover it. I think that will be it. And then the finals, also 2 hours, 6:30 on August 6, 2014. And by the way, that 2014 is important. Don't write down 2015. That probably won't be the right exam time. You'll be just a little bit late. Anyway, that will also be closed book notes, and that will not comprehensive. That'll just cover the second half. Okay? So those are the course the course features, the course overview, and I guess with that, well, it's almost noon my time, but if you're watching this during the class period, I guess it would be, I don't know, roughly an hour or so. I will actually today, since you'll be viewing this at night, I'll also take probably a shorter 10-minute break just so you can quick break on this. Okay, so why don't we now at least get started with the discrete time systems, some properties, things that you really need to know. Also having these some notes on complex arithmetic that you will need to know. It used to be I required that you, or in this class I use some complex analysis, complex variables, or what? No, not variables, actual complex analysis. And there are courses, some of the math courses teach that, or maybe some of the engineering. Not critical that you have that information now, but you have to understand some basic complex arithmetic issues. You should know, well, I'll talk about that in a few moments. Anyway, if you look on the Dan Blackboard under course content, I think it is, you will see the first set of notes. There are two sets of notes that I posted. I'll probably talk about both tonight, or today, or whatever time you're watching this. But there's a set of notes, EE483 sequence systems _1. Okay, so those are the set of notes. They're not very long because this is kind of a short overview of discrete time systems, but it's an important overview because, as you will see, all the basic concepts of digital signal processing, discrete signal processing, are covered in here. So I don't know how many of you have seen all this or not, but this is, or have exposure to this, but this is very, very important background material, and it's good to kind of get you started. So with that in mind, we'll start out with the definition. In this course, a sequence, we will deal with sequences, time sequences, etc. So by a time sequence or a sequence, what I mean is that is an index set of real or complex numbers. Yes, complex. So these will actually form what we call discrete time signals, okay? As opposed to continuous time, which if you've had the linear systems course, you've undoubtedly have run across. But these are discrete time signals. And by discrete time signals, it could either be a real valued signal, it could be complex, okay, either one. But in any event, it is an index set of real or complex numbers. By index, I mean it looks like this, x sub n, where again, x is real or complex, that's the signal, and n is the time index. So if you're used to continuous time systems, you might see and might have seen in the linear systems course 301 or something, I forgot the number, then you would see typically things written like this, x sub t for continuous time. Okay? But in this course, we're dealing with discrete time signals, so we will now be talking about, oh, I'm sorry, this is z. I think I need new glasses, z of n. So z of n corresponds to discrete time sequences or signals, okay? So n, that's what I referred to as the index. N is an integer, okay? N is an integer. What is the range of the integer? Minus infinity to infinity, Could be 0 to infinity, could be finite. Some signals later in the class we'll deal with are n is finite, just a snapshot. But whatever it is an integer, and typically it's a continuous integer. And generally, oh yeah, I should point this out. Generally, z of n, I can write it as some real signal plus j or I, imaginary square root of minus 1, times y of n. Okay? So generally, z of n will comprise two real signals, both real and the imaginary component. And here would be an example. So you might say, where do these discrete time signals come from? Well, it could come from a lot of places. If you're working on computers, probably they would be coming from memory, or like in Matlab, you'd be generating these in memory. Very simple. In an actual hardware system, they also might be stored in memory or on your in a computer, but they might be coming from something we call an A to D converter. A to D is an analog to digital converter. Okay, A to D, or yeah, analog to digital. Okay, so that's another perfectly valid place these signals could be coming from. Converter. And so in this case, you actually, it would kind of be a mix of both worlds, both the continuous time, you might have a signal x of t going in, and the discrete time. Now in this case, what happens is you sort of let t, oh, I should point this out too. T is going to be equal to, in this case, t here will be equal to some integer times a delta t, okay? Delta t. What is delta t? Well, that's typically one of the parameters that characterize an A to D converter. Namely, the A to D converters require something called a sample frequency, f sub s. And this is called the sample rate. Sample rate. This is in, here, let me say this. F sub s, and that's equal to sample, it's called the sample frequency or sample rate. And that's in units of hertz. And by the way, this is also equal to 1 over delta t. So if Fs is in units of hertz, delta t is in units of time, seconds. So, this, wherever I wrote it, t equal n delta t. Delta t is the sampling interval. What that is that's the time duration between when samples are collected from this A to D converter. And the output of the A to D converter is x of t is in, it's x of n delta t coming out, see? And that is a perfectly valid sequence that we can use. That's the digital out. So these are very useful devices, these A to D converters. For hardware systems, use these. So we'll talk about these in more detail later in the class. And by the way, just for completeness, I should tell you, there's really basically two parameters that characterize these A to D converters. One is the sample rate, okay, I should say in hertz. One is the sample rate, which is in hertz, and 1 over the sample rate is the time interval between samples when this thing collects a new sample. The other parameter is the number of bits. Is this an 8-bit A to D converter, 12-bit, 16-bit, etc.? So that's another parameter. And again, later in the class, we'll talk about some of these parameters. I have a whole set of lecture notes on A to D converters. So we'll come back to that later. But in any event, that is some examples of discrete time sequences, or at least a definition and how they can be generated. Now let's look at some specific examples, however they're generated. These are very important examples. Some are very simple, some are a little bit less so, but They're all standard discrete time sequences that we will use or we will come across in the course. The first one is the simplest of all. That is the discrete impulse response. Okay, so that's just basically delta of n. Okay, delta of n, which I use for the discrete impulse response. We use that all the time, and it's basically just, well, here's a plot of it. Okay, it's just 1 when n equals 0. And it is 0 every other place. Okay, very simple little function, but a very, very important function. By the way, since this is the projects are Matlab, simple way to generate this. I don't know. This is something that I use. There's other ways. Pretty simple. What I do typically in Matlab, if I wanted to generate this, because obviously you, in this class you will need at some point or other to generate this impulse response to probe digital filters, etc. You can use these commands. These are actual Matlab commands, where n is the length of the impulse response, and you will see it. You will find out in Matlab that the length of this impulse response, n, can be, sometimes you need it to be pretty large to see the full extent of the impulse response, especially if you're trying to estimate the impulse response of a digital filter. Even in Matlab, some of the digital filters, remember what I was calling the IIR, infinite impulse response filters, you have to have a large enough number of points, because in Matlab everything's finite. It's not really. In mathematically, it is defined to be infinitely long, the impulse response. But in Matlab, it's only finite. Oh, here's the other part. This is how I generate z of 1 equals 1. Okay, so you overwrite the 0. This is a simple way to generate the impulse response. But by definition, in Matlab, the length of the impulse response has to be finite. So if you're trying to use this impulse response to probe a digital filter, you know, you typically will have to make n large enough so that you can see the full extent of the impulse response to the digital filter. So we'll talk about that later as I talk about some examples of digital filters in the class. Okay, so anyway, that is the impulse response. Here's another one. This is kind of an interesting one, even though it seems pretty simple, but kind of help you with understand a little bit of the differences between between digital signals and continuous time. This is the discrete sine wave that's used a lot in this class, obviously. And the discrete sine wave is normally defined by, I guess, 3 parameters. Okay, one is the phase, phi, one is the amplitude, one is the frequency, which I'll have another comment about in a minute. And notice it's a function of a discrete time index. Now, one point I should make, in continuous time, presumably many of you have dealt with the discrete and the continuous, or maybe just the continuous. But in continuous time, we would have also a continuous time sine wave, and that would look like this. Cosine of, now I'm going to call it 2 pi f naught t plus phi, okay? That would be continuous time. But there, you look at it and you think, well, these two are very similar, and they are, but there's some subtle differences. Like, for instance, see that f naught? That's a frequency. Again, in units of hertz. Okay. What if the sine wave? What if I used a 1 hertz? No problem. What if I used a megahertz for f naught, a million hertz? No problem. What if I used 10 to the 12th hertz? No problem. T is continuous time. So And if you did a 10 to the 12th hertz, you would find that, lo and behold, I think that's terahertz. Gigahertz is 10 to the 9th. Anyway, you would find, lo and behold, that you would get, if you put this in, you get a valid continuous time sine wave. And if you looked at the spectrum, we'll talk about that later, you would see, a well-defined spectrum. So basically what I'm saying is there is no limit on F naught. Okay? By the way, interestingly enough, F naught could be negative here. You could have F naught equal minus 5 hertz, say. And then it would be cosine of minus 2 pi, 5 hertz t plus phi. But because of the symmetry of the cosine, that would be also equal to cosine of 2 pi f naught t minus phi. So putting in a negative frequency just changes the phase, but makes it plus to minus. But other than that, there's no restriction. No limit on f naught. Minus infinity, less than f naught, less than infinity. Okay? And every different f naught, you get a distinct different answer. Okay. That's not the case in our discrete world. Okay? In the discrete world. Well, first of all, let's let z of n equals x of n delta t. Let's do it. Let's sample this thing. Okay? So that's going to be a cosine 2 pi f naught, can you see, okay, delta t times n plus phi, okay? So it does look like this. Here's my phi, okay, that's the same as continuous. Here's my amplitude, that's the same as continuous, but what is this stuff in here? So let me rewrite this as omega naught n plus phi, okay? And omega naught will equal 2 pi times f naught times delta t. That's the sampling interval. I can also write that as delta t. I can write that also as 2 pi f naught over f sub s. Well, the first thing you notice is this is dimensionless, okay? Unlike our continuous time case. This is dimensionless. The second thing that I want you to know is, but you're saying, yeah, but it's still unlimited. F naught can be anything. Yes, it can, but, and here's the subtlety in this. Okay, suppose, let's see, I don't know, let's suppose for the heck of it that, let's suppose F naught, I will choose this, will equal, let's let it equal, I don't know, Fs over 4, okay? Let's say Fs over 4. That implies that omega naught is equal to 2 pi times 1/4. That would be pi over 2, okay? No problem. You get a nice discrete time sine wave. And by the way, I should sketch these in. You get something like this. Even though when I draw these, what I'm actually drawing, that's actually the envelope of the sine wave. That's a continuous curve. The actual discrete time sine wave values are going to be these little dots, see? And interestingly, in Matlab, if you have a discrete time signal, you can plot those. If you have a discrete time signal, you can plot those using the plot function, but that will kind of linearly interpolate between samples, or you can use stem. There is something called the stem function, z, stuff like that. You could generate these plots. So, anyway, but I digress. So let's say you get this omega naught's pi over 2, so that implies that that z of n is equal to a cosine pi over 2 times n plus phi. Okay, no problem, and you get well-defined values. Aha! Now let's suppose I'm going to do something. So that's Fs over 4. Right. Now let's so that's example 1. Here's another example, just to kind of show you the subtleties here. Suppose F naught is equal to Fs over 4 plus Fs, okay? I'm just adding an Fs. So if Fs were a megahertz, Fs over 4 is 250 kilohertz plus a megahertz, all right? Again, in continuous world, that's a different sine wave. But let's see what it is in our discrete time world. So that implies that omega naught is equal to 2 pi, it's pi over 2. So omega naught's 2 pi F naught over Fs. That's going to be F naught over Fs will be 1/4 plus 1. Plus 2 pi. Let you check me out on that, but that's what omega naught is. Now let's take a look. Z of n. Now, okay, Z of n is equal to a cosine pi over 2 n plus 2 pi n plus phi, okay? It's a different sine wave. Well, yes and no. I mean, it looks different, but it turns out, remember, the sine waves are periodic in 2 pi. It's just equal to our O friend that we came up first, pi over 2 n plus phi. So, what's the takeaway from this? The takeaway is that basically F naught is limited in the sense that if you increase F naught by adding, multiples of Fs or partial multiples, you're not going to change the value of the sine wave. I took two cases. Two cases, F naught was different. Clearly, F naught was different in hertz, but the discrete sine wave was, sorry, let me got so excited on this stuff, I dropped my pen. But anyway, so there is, in essence, a limitation to the frequency that in the discrete time world. So more to come back on that, but there are, like I said, there are subtleties in this. Okay, what is, all right, but let's continue. So that's a sine wave. That would actually be a real discrete time sine wave. And we will also use a lot in this class complex discrete time sine waves. And they look similar. They look like this. And in this case, there is something called the de Moivre formula. I'll mention that. I kind of, well, here, let me just say this. I got to watch my time. In these notes, here, I have an appendix. I encourage you, if it's been a while since you used complex arithmetic, please review. It's only a page and a half, and it's got everything you need to know in this class. But get familiar with this if you don't know this cold already. You should know most of this cold. It's just simple complex arithmetic. But in any case, well, here, it's not de Moivre, it's the Euler identity, okay? So all the complex manipulations, the arithmetic, all of them were covered in this page and a half of notes at the end of this first set of notes on discrete time system. So anyway, this is the complex version of the sine wave, and by the Euler identity, it can be written as two. It can be written as a real sine wave, discrete, plus an imaginary sine wave, the imaginary part. Sometimes this is called the in phase for you hardware folks, and this is called the quadrature. So sometimes if you've heard people say, hey, I have a sine wave in phase and quadrature, that's kind of what they're talking about. And you notice that they're exactly, the cosine and sine are the same, except there's an additional phase shift of 90 degrees. So in any case, that is the deal on that. And by the way, if you wanted to compute the complex absolute value, that's defined to be the square root of the real part squared plus imaginary part squared. That's the complex absolute value. If you work it out, that would be simply A. It'd be simple to tell from this, because the complex absolute value of e to the j anything is 1, or you can see it from this using the identity that cosine squared plus sine squared of x is 1. So anyway, again, I encourage you to please go over Appendix A. It's very short. There's also what I call the geometric series. Those are kind of like, if you recall, in continuous times, you probably had continuous time. You would have something called x of t equal e to the minus alpha t, like an exponential. We have the same thing in discrete time signals. This is discrete time, very much the same. It's just you deal with discrete time index. So here would be, for example, what is called a right-sided sequence. This right-sided sequences are simply sequences which are 0 for n less than some n naught value. Here I've chosen one where n naught is 0. So this is a right-sided or one-sided geometric sequence, and it looks just like the continuous time. It's, well, I shouldn't say it looks exactly like. It's a little bit different, but it's alpha to the n greater than or equal to 0. Typically, the magnitude of alpha is less than 1, but it could be real or complex, but it doesn't have to be less than 1. We will deal with, when we talk about the Z transforms, we will permit signals that actually blow up. You haven't seen those before in continuous time, but you will here. So anyway, and by the way, we typically note that alpha can be written as e to the minus beta. You say, what's beta? Well, take the natural logs of both sides. So it turns out beta is minus the natural log of alpha. So for any alpha, you can write it as e to the minus beta, where beta is the natural log, equal minus log alpha. And you can rewrite alpha to the n, therefore, becomes e to the minus beta to the n. So now that looks a little more like the continuous time signal. So, but it is discrete time because it has a time index. What else might look like this? As I said, there's really not a whole lot of stuff here that we need to something else look at. So you might get a plot like this. Here's another one. This is the same except it's left-sided. And we will also deal with those. Typically in continuous time signals, you don't worry so much about left-sided sequences, especially impulse responses. But for this class, we will consider both. And here would be an example of a left-sided sequence, okay? Which can also be written as, if you want to use this notation, we will use this u to the minus n, okay? Where I should have pointed u of n is another one. U of n is defined to be 1 for n greater than or equal to 0, and 0 for n less than 0. This is called the unit step function, or unit step sequence. That's kind of like the delta function. Again, another building block. In fact, if you difference u of n minus u of n minus 1, it turns out you will get the delta function. Okay, so they're all related. But in any event, so that sequence goes backward in time. And a left-sided sequence, kind of like the right-sided in that it's any sequence who vanishes for n greater than n naught. It's identically 0 for n greater than n naught. In this case, n naught is 0. But you can even have double-sided sequences, okay? Where in this case, you know, it's two-sided. What's a simple example of a double-sided sequence that we've already seen, that you already know in the class? Double-sided. Example. Okay, what? It's that one we just talked about. Z of n is equal to a cosine omega naught n plus phi. That's a perfectly valid example of a delta of a two-sided sequence, or the complex sine wave. Okay. So anyway, get all these different types of sequences, and if you want, you can create new sequences by summing sequences. We'll talk about that later. So here's an example. Here's my first sequence. That's the initial primary sequence. And then here's the secondary derived from that. Z of n is equal to summation k equals 0 to n. This is like integrating. This is sort of like k for n greater than or equals 0. And 0 for n less than 0. This would be another sequence. This is sort of like in our continuous time world, y of t equal the integral from minus infinity to t of x of tau d tau. You know, these are sort of the similar, or maybe even better from 0 to t, something like that. Okay. By the way, I'm going to take, in just a second, I'm going to take a short break. Let me show you another example, and by way of doing, I can point out an identity that we will use in the class. Alpha to the n times u of n. Okay, that's one we just talked about. That's the right-sided geometric sequence in this example. But I want to take it a step further. So let's see, what does this look like? K equals 0 to n. X of k, right, of course, for n greater than or equal to 0. So let's take a look at this closer. So this is going to be summation k equals 0 to n alpha to the k. Turns out we can write that in a closed form expression, and there is something called the geometric sum formula. Geometric sum formula, which we can apply it directly to this. And that basically says if you have an exponential or a geometric sequence like that, you can sum it exactly using the geometric sum formula, and you always get it to be 1 minus alpha. In this case, the upper limit, you always go n plus 1. So like if this went to L minus 1, that would be 1 minus alpha to the L, divided by 1 minus alpha. So it's a nice, cute little formula that that we will use. You don't have to memorize it, but basically, and then there's a lot of specific cases of this where you can actually generate a lot of sum formulas from this. But this is the basic one, and we will use it. So like I say, you don't have to memorize it, but you have to understand what that means, geometric sum formula. Okay, so look, this is probably a good point to take a break. So why don't we take today, since my class is a little bit shorter, got stuck in, this is unbelievable. You will not believe this. I got stuck coming in here at 11 o'clock in Los Angeles traffic. Can you believe that? It's normally freeways are wide open. But anyway, I will take a short break, probably 10 minutes, and I will see you. I will come back. This session today is probably shorter than usual, but anyway, I'll see you in 10. Is that okay?
Yeah, that's great.
Okay. Okay. So that is what we talked about is some of the basics of certain types of discrete time signals. Now let me mention some theorems relating to discrete time systems. And all of this is like I said, it's all basic, it's pretty straightforward, but it's just important that you make sure you understand this stuff cold, because it forms the basis for all of our future work in DSP. And a lot of this, what I'm telling you, is it has counterparts in the continuous time world. Okay, here's kind of a simple concept, but it's used a lot, and it is what we call the representation theorem. And essentially, in the continuous time world, it just says that continuous time, it just says that x of t, if you use Dirac delta functions, is the same thing as x of tau times delta of tau minus t, d tau. So it's kind of an analog, well, I guess I can call it an analog of that continuous time theorem. And essentially what it says, if I have a sequence, I can write this as summation k, and this will become important when we talk about, in just a moment, certain types of discrete time systems. The systems called linear time invariant systems. And that's all it really says. Obviously, it's trivial because delta of n minus k is only non-zero, I should say, when n equals k, and so you get z of n out. So it's just kind of a basic identity. It's also analogous to, 1 times x is equal to x. That's the idea in the signal domain. And so or incidentally, I could write it as z of n is equal to z convolved with delta of n. Okay, this is called discrete convolution. It's like in the let me write that, discrete convolution. It's analogous to the continuous world. This would be considered to be, in a continuous world, a convolution of x and a Dirac delta function. Maybe I should call it D for Dirac, so distinguish it between our delta function. And similarly in the discrete time world, this sum, that's called a discrete convolution between z and delta. So that identity, x equals 1 times x, it's kind of analogous to z equals z convolved with delta. So anyway, that's what the representation theorem here. This is just a graphical illustration of it. But we use that because that sets us up to discuss discrete time systems, especially systems with certain properties. Okay, so first of all, what is a discrete time system? And again, if you've had linear systems class, and you've talked about this in the continuous time world, and it's the same thing in the discrete world. A discrete time system is basically a black box. I call it here T, which takes in input signals and outputs output signals. That's basically what it does. So it accepts an input sequence and it produces an output sequence. There are many variations on this theme. You can have systems like single input, and you can have multiple output, y1 ... y sub n. Those are called, by the way, these are called MISO, standing for multiple input. No, I'm sorry. SIMO would be an example. Single input input and multiple, oh yeah, single input, oh yeah, of course, forgot for a second the acronym. Yeah, single input, multiple output, SIMO, okay? Output. Or there could be MIMO systems. You possibly have heard of those in a communication context, where you have X1, let's call that L, and then output would be Y1, YM. Okay, I'll make that an M too. T, which is MIMO, multiple input, multiple output. So there's all different types of variations on this, but this is the basic one, which takes a single input and produces a single output. And what are some examples of this box with a T in it, capital T? Examples abound. There's digital filters. T could be a neural network. Basically, T can be anything. It can be linear or nonlinear. It can be with memory, or what we would call memoryless. That's one to get used to. Memoryless. So an example of a T with memory would be the digital filters. We will see. There you actually, the ones with memory means that to produce the output sequence, you need to have past values. It isn't just enough to have x of n, but you have to store inside of this past values of x of n to produce your final output. So those are systems, discrete time systems with memory, or we could have discrete time systems without memory, memoryless. Like for example, there would be I don't know, y of n equal x of n squared. Okay, that would be a memoryless nonlinear system. So anyway, it can be almost anything you can think of. That could be a system. It's sort of like the Seinfeld episode where they were determining, Jerry and George were determining what type of sitcom they could do, and they came up with the idea of a sitcom about nothing. You go to work, get dressed, nothing. Okay, well, this is about something about everything, but T could be almost anything, and that would be a system. By the way, I should tell you, I watch too much Seinfeld, old reruns. Anyway. So here are some types of discrete time systems, specific types, specific examples, and some definitions. Linear shift invariant, or time invariant. The book, I think, uses time invariant. So that's LSI, or sometimes I think in the book LTI systems. So what are LTI or LSI systems? Well, by the very name itself, they're systems that are linear and time invariant, or shift invariant. So what do I mean? First of all, what is linear? Linear simply means that if I have two inputs and I add them together, again, this is single input, single output, I guess you'd call that SISO. So if I have an input like this, let's call that x1, introduce you to a little block diagram stuff, and I multiply it by alpha, and I have in here another signal, x2 of n, and I will multiply that by, let's call it beta. So what comes out here is alpha x1 of n, and what comes out here is beta x2 of n. That's the little circle with a cross is my notation for multiply. Now what I do is I take both of these guys and put them into a summing junction to produce alpha x1 of n plus beta x2 of n. And now I put that in, feed that into a system T and output y. Well, what this says is that if the system is linear, then and you happen to know what the response of the system is to x1. So in other words, here's another diagram. x1 goes into the same system. Out comes y1. x2 goes into the same system, and you know its output, T, y2. If the system is linear, then the response to a sum of the inputs multiplied by alpha and beta is equal to alpha y1 of n plus beta y2 of n. Very, very, very important property. Most of the systems we deal with in this class, if not all, well, maybe there'll be some homework on some nonlinear, but basically they will all be linear systems, and linear systems obey that property. So basically it says that the response of a linear system to the weighted sum, I'll call it, of two inputs is the weighted response to each of the individual inputs, okay? So very, very important property, and we will use that property quite a bit. So that takes care of the time invariant. What is the shift invariant? What is the shift invariant property? Well, the shift invariant sometimes, in fact, I will say a lot of times, a little bit more difficult to get your arms around as a concept. But basically what it says is that if I have a system, okay, x of n, and again I have my response y of n. Okay? Now, what if I do this? Actually, this lets me introduce another notation we do in block diagrams. What should I call this? Bear with me a second. Just got to check something that what did I call this? D. I'll just use that. D. And then that goes into T. And out will come, I don't know, we can call it y1 of n. So x of n goes in. It goes into this box called D. What is D? That's a one-sample delay. The output of D stands for delay, is a one-sample delay. We will have different terminology for delays or delay blocks in DSP, but this is as good as any. Then it goes into my system T, and output comes y1 of n. So the question is, what is y1 of n? Can we somehow relate it to y of n? And the answer is yes, you can, if the system is linear shift invariant. For LS or LTI systems, or LTI, linear time invariant, either one, same meaning, y1 of n is equal to, you have that response y of n minus 1, see? So basically, both of these theorems, or rather not theorems, but definitions, mean that if you have the response of this linear time invariant system to one input or separate inputs, then you can combine those and construct the response to time or linear versions, linearly added versions of those inputs. And clearly, this is just a one sample delay. That's a unit delay. If the delay was greater than 1, maybe it was 10, or it could even be a minus 1. You know, you could have a negative delay out into the future. However it is, then you will have this property that the response of the system with a delay of n naught samples is the response with no delay, but delayed by n naught samples. So here it is. Okay? Two very, very, very important properties or definitions to keep in mind. I even had a little, this is interesting, I had a little diagram of this. Let's see what I wrote here. Okay, I'll come back to that in a second. I had a little diagram here to illustrate all this graphically. I said, suppose this is my input, x of n. Okay, it just had these, I don't know, 4 samples and then a bunch of zeros, say. Suppose the response of that system looked like this, okay? So it looked like this. It was these output samples, zeros. Now, suppose, that's interesting. Suppose x of n minus naught look like this, so that should be the same as this, just delayed by n naught samples. Then, you know what? If the system is shift invariant, we take this response and just move it over n naught samples to produce this. Okay? So that's what a shift-invariant system example might look like. A linear shift-invariant or linear time-invariant satisfies both of those properties. Namely, it's linear and it's shift-invariant. Here's an example, by the way. This is an example of a frequency. It's an interesting example. And again, now I'm just introducing some of these. We'll come back and define what these are later. But it turns out if you want to do frequency conversion, this is an example of such a device. It's a very simple example. It says T of x of n, in this case, would equal a of n times x of n, where a of n is a sequence, another sequence, okay? So basically, you're taking a of n, or I'm sorry, you're taking x of n, and you're simply multiplying it times some sequence we will call a of n to produce your output, a of n times x of n. That's a perfectly valid system. So let's see if it's linear. Linear, let's check it out. If you had t of x1 plus x2, well, that's going to equal a of n times x1 of n plus x2 of n. So clearly it's linear, right? So that's going to be the response to each one. I will call them y1 of n plus y2 of n. So that implies linear, yes, sir. So that's a perfectly well-defined linear system. But let's look at shift invariance. Shift or time invariant. Is it variant? And we will see in just a second that no, it isn't, that a of n messes things up as long as a of n is, if a of n is not a constant, because look, check it out. T of x of n minus n naught, what's that going to be? Well, by definition, that's going to be a of n times x of n minus n naught, okay? So that's just by the very definition. Now, let's look at y of n equal a of n times x of n, and let's look at y of n minus n naught. Now, those should be the same if it's shift invariant. But you will see is you replace n with n minus n naught in here, okay? And that's going to be a of n minus n naught times x of n minus n naught. So if for general a of n, which is varying with n, then that implies that it's not equal to t of x of n minus n naught. Therefore, it's not shift invariant. Okay? So that's a simple example of a system which is linear but not shift invariant. Linear shift invariant systems satisfy both. They're both shift invariant and linear, obviously. Okay? So let's look at some properties of linear shift invariant systems. I should tell you, most of the systems we study, not all, because we will talk about frequency down conversion systems and other systems, but most of the systems that we study, the vast majority, are linear and shift invariant systems. Now, what's so good about linear shift invariant systems? Well, let's take a look. Any linear shift or time invariant system can be characterized in terms of its impulse response. Remember I mentioned before, finite impulse response, infinite impulse. The impulse response was what I talked about. What is the impulse response of any system, right? What is the impulse response? Well, that's pretty simple. That's the response of a system to an impulse. So if you have, which I'll rewrite this, sometimes I duplicate things. If you feed into a system, our friend the delta function, the output h of n, that is defined to be the impulse response, okay? So that is what I mean by the invariant. Pretty simple. It's just the response of a system to an input impulse signal. Okay. Well, it turns out this h of n plays a very, very important role for LSI systems. So this is key for LSI systems. I guess what I was saying earlier, hopefully you will concur this is a lecture about something instead of a show about nothing. I've been watching definitely way too much Seinfeld. Anyway, and linear shift invariant system, okay, so this is just general, but it's a key concept for linear shift invariant systems. A linear shift invariant system can be characterized in terms of its impulse response. So this is a general result for the linear shift invariant systems, and it says for any LSI system, I can always write the output as a function of its input like this. X of k times h, a very, very important result. Or I can also write that as x convolve, a discrete convolution with h. Okay? Very important concept. For any linear shift invariant system, if I know its impulse response, I can generate the output for any input, x of n. One thing I want you to notice, this is not memoryless. This is a memory system. So I didn't say anything about linear shift invariant systems requiring no memory. They do. General, an infinite amount of it. Look, because you need samples of x from x of n all the way plus or minus infinity. You need basically the entire bit of samples. But once you have those into your memory, you've got y of n. Okay? So that's a very, very important concept for linear shift invariant systems. Why is this true? That should be the question you would ask, unless you already know the answer. Oh, this is an interesting. Here's an example pictorially that I drew. So in this example, x of n is my delta. Yeah, this is kind of an interesting example. Here we're going to feed delta into our system. And this is just an example, and h comes out. Here's a little example where here's my delta of n. And then look, in this example, this is the output. Now, the interesting thing in this little picture that I drew is that everything's 0 with the input before time n equals 0. But if you look at the output, this is a perfectly valid linear shift invariant system. If you look at its output, you will find that it's not 0 for n less than 0. Systems like this, and these are linear shift invariant, they can be perfectly well-defined linear shift invariant systems, but they are called non-causal systems, whether they're linear shift invariant or not. So anyway, I just thought I'd throw that out there. We'll come back to that notion in just a few moments. So here is why I said this is true for any linear shift invariance. Why? Okay, this is the proof. I've written it out for you. You first of all notice that, guess what? We can use our representation theorem. Very nice, huh? Delta equal x convolved with delta. Any x can be written as x convolved with delta. It's like for any x, 1 times x is equal to 1, where delta is like the 1. So that is our representation theorem. Told you we would use it. It's pretty simple. Kind of trivial, actually. But here's our time to use it. So now let's look at the response of a linear shift invariant system to x of n. Well, again, the response is I can write x of n like this through the representation theorem. And now check it out. Since this is a linear shift invariant system, then I know that I can write this as, if this is LT, if this is LT, I can write this at, now, the only thing that depends on time is this delta. So I can write that this can be thought of as a constant, okay? X of k can be thought of as a constant times this time-varying function. So we can write this as summation minus infinity to infinity. Here is the constants, x of k times t of delta of n minus k. Okay, and this is repeated on the next page. I'm just kind of showing you in real time here. And this is because the system is linear. Linear. We can go a step further. We can say, well, wait a minute. Because the system is shift invariant, I can also write this k, x of k. Can you see this? Yeah. Okay, because the shift, remember, t of delta of n, without the k, is just h of n. But because the system is shift invariant, t of delta of n minus k is the same as h of n minus k. And that's because system is shift invariant. Okay? So there you have it. That's why I'm saying the linear plus shift invariance is a very, very important property. It allows you to determine the output of any input just in terms of the impulse response. So there it is, QED. So that's what the next, again, like I said, I repeat this on the next page. So there it is. Very, very important concept for linear shift invariant systems. So make sure you, it's very straightforward, but make sure you understand it, because it will be needed through the rest of the course. Because like I said, a lot of the systems, in fact, the vast majority of the systems we deal with are linear time or shift invariant. Okay? But there are some other important system concepts in general. Two more important general systems concept. In other words, not just linear shift invariant. One is, although for shift invariance, linear shift invariant, some of these simplify a little bit, but in any event, okay, stability. What is a stable system? That's very simple. A stable system is for any bounded input produces a bounded output. Okay, this should be a prime. You can't hardly see that. Okay, so if I have an input that's bounded, gets no larger than plus or minus m, then the output, if it's a stable system, will get no larger than maybe some m prime. Okay, m and m prime doesn't have to be the same, but both inputs and output has to be bounded. Okay, so that's just general stability. What about, I have notes from last summer. I just want to make sure I haven't missed any detail. Okay. Bear with me. Okay, yeah, I'll use that example. Okay, a linear shift, okay, so this is one of the examples I meant. Okay, so that's true for any system. That's a general definition. Any general system, okay? But what if if the system is linear shift invariant? Then it's very, very interesting. If the system is linear shift invariant, then it turns out to check for stability, all you have to look at is the impulse response. So again, linear shift invariant systems, everything goes back to the impulse response. Namely, the impulse response has to be, what would we call it? Absolutely summable. Okay, in other words, the absolute value of the impulse response has to be bounded. A sum from minus infinity would have to be bounded. As an aside, if h of k is equal to 1 over k times u of k, it turns out then system is not stable. I'll let you look at that. Okay? Is not stable. Okay? That's an example of not stable system. But if h of k is absolutely summable, then the linear shift invariant system would be stable. And that's actually an if and only if. And I show something else here. Hey, bear with me here. Okay, let me, well, here, I'll discuss that. Okay. First show that if, anyway, this is approved, you can sketch out. Now, I want to show you an example. By the way, all this writing that I'm doing on these notes, I scanned these notes, so they will be available on DEN. After today's lecture, I'll make sure these are available, as I will the tapes if I can, or tape of the day's lecture. I'll try to make it available now so you can kind of get a picture of what the class is. But again, this is meant to be taped for the first class, May 21st. So here's an example. This is kind of an interesting question. Example. Suppose we had a linear shift-invariant system, and our input, instead of the delta function, is our friend the complex exponential. Okay? Looks like that. So what is y of n? What's that look like? And this is a linear, well, well, in this example, t of x of n, let's suppose, let me put it this way. This is not, well, here you'll see. Suppose the output of the system is e to the j omega naught n, okay? Well, it turns out that could be linear. Could be linear. You know, it depends on, is that true for all x of n, but that could definitely be linear. But how about this one? How about this example? Suppose y of n equal t of e to the j omega naught n. This is a problem that I give actually in an exam, a kind of a true-false type question. Suppose the output were a times e to the j omega naught n, just like here, but plus I'm going to add in b times e to the j omega naught times 2n, okay? So it's basically a sum of two sine waves. The frequency of the second is double the frequency of the first. So the question is, could this t be linear? Okay, that's a question. Like I said, that was a question I had on an exam a long time ago. And as it could be linear shift invariant, I should say. And the answer, surprisingly, is no. No. The answer is no. So let me get another piece of paper here. So for this example, so y of n equals t times e to the j omega naught n. And I'm saying that's equal to a e to the j omega naught n plus b e to the 2j omega naught n. Okay, t cannot be linear shift invariant. Maybe I will let you think about, that's all right. Why? Because if t is linear shift invariant, if t is LSI, then we know that, if it is linear shift invariant, then y of n is equal to h convolved with x of n. And for this case, that's going to be summation, I will call it h of k times x of n minus k. By the way, as an aside, in that earlier, just a few moments ago, I wrote this as summation, well, forget that. I'll just, clearly this can be written either way. X of k times h of n minus k. Okay, you can write that either way. I prefer this way. I prefer where the impulse response or whatever it is has the k, and then the n dependence is on my input. But in any event, either one of these are identical by change of the index, okay, variable. Anyway, to continue, so that's going to be summation e to the j omega naught. In this case, remember, the input's e to the j omega naught n times h of k. Remember that. Okay? So if t is linear shift invariant, then we can write the output for any input. In this case, the input's e to the j omega naught n. So check this out. This is equal to, the n doesn't depend on k, so I can write that out. And not n times summation k e to the minus j omega naught k times h of k. Later, next time, we will see that this is actually the discrete time Fourier transform of h, but for now this is just some constant. It doesn't depend on n. It's just a sum. So I'll call that c. So this is c times e to the j omega naught n. That turns out that's QED. Why? You don't see an e to the 2 j omega naught n, right? You don't see an e to the 2 j omega naught. You only see e to the j omega naught n. So, very simple way to look at linear shift invariant systems. If you have a linear shift invariant system and you send a sine wave, or you input a simple sine wave, this is a good way to test to see if it is a linear shift invariant system. So if you have some unknown system, you want to determine if it's linear shift invariant. One way to do it is input a sine wave. If you're getting out the sine wave plus a different frequency, not linear shift invariant. If it's linear shift invariant, you will only get a sine wave out multiplied by an amplitude and phase as c, but only a sine wave out the same frequency. So anyway, very, very interesting implications of linear shift invariant systems. Causal systems. Actually, we've already covered an example of a system that's not causal. A causal system, a system is causal if the output y of n only depends on present and past values of its input, okay? Only if the output depends on present and past values of the input. Where am I? Oh, yeah. So I wrote that like this. So in other words, the output, it could have memory, that's fine. In fact, these systems generally do have memory, as I've already pointed out. But if the system is causal, the output can only be a function of x of n as well as and possibly x of n minus 1, x of n minus 2. It cannot be, y of n cannot be a function of x, for instance, x of n plus 1, see, if it's causal. Now, if it's non-causal, no problem. So in other words, the output at time n can't know about what the input is at a future time. That's non-causal. I'll go back to my previous example. That was the one I sketched out. This example. I'll go back to this one, okay? This one. This is a non-causal example because because the output of the system, it's like it anticipates. See, this is my delta function of n, but before n equals 0, everything's 0. But this is somehow anticipating that some value of x or something into the future. So this is definitely non-causal. You can't have an output before the input goes in, okay? So that's a consequence of a non-causal system. So this is clearly non-causal. Something's funny in that it's like a precursor of this input. Okay, what about a linear shift invariant system? This is a general definition of causality, this right here, general. So what about a linear shift invariant system? What can we say about one of those? When is a linear shift invariant causal, or how can we check for causality? Well, that's pretty simple. If the system is linear shift invariant, just take a look. well, look at this. I guess I won't rewrite it. Okay, remember that. If the system is LSI, Y can be written as a convolution of its impulse response with the input. Just expand that out. Expand that, like I've done here. It's equal to ... plus h minus 1 times x of n plus 1, h of 0 times x of n, h of 1 times x of n minus 1, ... Well, the point you can see is that the only way for this to be a function of present and past values of x is if the h is 0 for n less than 0, okay? So, for an LSI, or let's say it this way, an LSI or LTI system is causal if h of n is equal to 0 for n less than 0, okay? So in other words, the impulse response of a causal linear shift invariant system is one-sided. In fact, I'll go further than that, it is right-sided, okay? So, again, linear shift invariant systems have a lot of really, really nice properties. And let me end, no, I have a little bit more time, forget that. So that pretty much are these notes. Again, I encourage you to look at the appendix, what I call my primer on complex arithmetic. It's only a page and a half, but it covers pretty much, it has all the formulae that you need to do this class. Pretty much everything can be derived from these basic identities and formulas. So please review these. It's only a page and a half. But review these. Make sure you understand these. If you've had a course in complex variables or complex analysis, then of course these are trivial. But even if you haven't, I contend you can still do well in the class, but you just have to understand these basic properties. And if you got any questions, you let me know. Hopefully you have seen all that. Okay, so let me conclude this section. Actually, I think I have time to get started on the next section. But let me conclude this section on discrete time systems with an example, okay? Now, as I said, time invariance or shift invariance is a little bit more difficult for people to get their arms or head around than linearity. Linearity is straightforward, but shift invariance, and I give you one example of a system that's not shift invariant, a pretty simple example. Let me give you a second example. This one, for me anyway, a little more, you gotta think about this one a little more. Suppose my system output, x of n, to my input look like x of n squared, see? Perfectly valid system. I will call that y of n. Okay, it's a perfectly valid system. What it's done is it has stretched time out by, so I have x of n coming in, my y of n will be x of 1, x of 4, x of 9, x of 16, etc. So it's kind of a weird thing. It's done something to time, it's basically, or discrete time. It's done something, it's stretched it or compressed it or something. So my question is, for right now, is it shift invariant? That's a good question. Well, let's take a look, and I'll show you a trick for analyzing this type of system where you have something like this going on. My question is, does this equal x of n minus n naught squared, which would be, by the way, y of n minus n naught. Y of n is this, so if I replace n with n minus n naught, that's y of n minus n naught. Would that be equal to t of x of n minus n naught? A little bit different than before. The way I like to analyze systems like this, I first do it in steps, 2 steps. First, I define, I know this may seem kind of crazy, but I define another function. Let's call that x1, and it will be defined to be this. It will be the shifted version of x. I will call that x1 of n. And now what I will do is, what would be my system response to x1 of n? See? Get the idea? So it's a little bit easier to deal with this. Well, that would clearly be equal to x1 of n squared, okay? Well, what is x1 of n squared? Keep in mind, see, what this is saying is that every time you have n, you replace it with, in this case, n squared. So what is x1 of n? Well, it's x of n minus n naught. So the prescription is I simply replace n with n squared in this x of n minus n naught, and guess what I'll get? I will get x of n squared minus n naught. So you see how this stuff, it gets, I don't know, for me, a little bit, you know, there's some subtleties in some of these examples. So the question is, again, y of n minus n naught. So this is the response to x by definition, t of x of n minus n naught. I just introduced x1 as kind of a little intermediate input sequence, or an intermediate sequence. But I did it, I introduced x1, you may wonder why, because I can see a little bit more easily what's going on. Namely, t of x1 we know is x1 of n squared by definition. Then if I look at what x1 of n is, all I know that all I have to do is replace n in the definition with n squared. And here's where n comes in. So that's all I have to do. That's why I get n squared minus n naught. But if you look at this, this is x of n minus n naught squared, like we discussed before. And now you compare these two, guess what? Sorry, they're not the same. Not the same. So this is not shift invariant. And I'll tell you something else about this example. So lots of very interesting, I'll show you something else. Suppose n let n equals minus 3. Guess what the output is? Y of minus 3 is going to be x of 9. Okay, so the output at some time, in this case minus 3, is a function of a future value of the input at x of 9. So this is not only is it not shift invariant, it's not even causal. So, very, very interesting. You make sure you go through these examples, and then you can start to become an expert at determining whether a system is shift invariant or not. And I can tell you right now, I will tell you at this point in time on May 21st, or actually May 9th, that on your midterm on June 25th, there will most undoubtedly be a true-false type of a question where I'll show you some sequences or systems and ask you if they're linear and shift invariant and all that. And I tell you, this is where a lot of times people get kind of confused. So make sure you understand this. You will see it again on the midterm in some form or another. Okay, so that is the, that does pretty much finish this section on sequence discrete time systems. I have a few more minutes, so I have enough time that I can talk to you for a few minutes about the second set of notes, which I am calling, let's see, make sure I got them all. Yes. The second set of notes that we will go over next time I see, or when I first see you, which is on the 28th, we will finish talking about these. But let me, I have a couple of minutes, let me at least kind of mention this, or at least introduce you to this. So I have another set of notes called linear LSI sys DTFT _2. And these are also, these notes are also, these notes are also posted on the Den Blackboard, so you can look at these. And I believe this is in Chapter 3, covers this, Mitra, section, I think either edition 4 or 5, it's the same thing. And this is called Characterization of Linear Shift or Time, Synonymous, Invariant Systems, and the Discrete Time Fourier Transform. So I promised you we would spend the vast majority of the time talking about linear shift invariant systems. From now on, if you see, if I bring up a linear, not a linear shift invariant, it'll either be on homework, a question or possibly on the midterm through the true-false thing I mentioned. Okay, so let's talk about the most important class, not the only class, but the most important class of linear shift-invariant systems in DSP. I told you they can be characterized in terms of their impulse response. Well, this is a different way of characterizing an important class of linear shift-invariants. Can be described through something called the constant coefficient linear difference equation. Those will form the basis of all of the digital filters, I can say, or almost all the digital filters we will discuss in this class. Constant coefficient linear difference equations, or I sometimes call them LDE. And these are sort of analogous in continuous time to differential equations, which presumably you've had those, diff EQs in continuous time systems. So again, your systems class, like the 301 or whatever it is, probably talked a lot about differential equations in continuous time. Well, in our discrete time signals, instead of differential equations, we deal with difference equations, not surprisingly. And here's a very general form of a difference equation. And I'll have more to say about these later on. But basically, what they say is that, well, I write it like this. Summation A of ky of n minus k is equal to summation b sub m x of n minus m. So the time shifts of x, time shifts of y, multiplied by coefficients a and b, where x would be the input, y is the output. Or equivalently, what I do is I assume, this is normally the form that we use, that a naught is equal to 1. What is without loss of generality? It's simple to include a non-com, but just for simplicity, without loss of generality, we will make a naught 1, and you end up with this difference equation. Okay? This, my friends, defines a recursive, this is a form of or IIR, infinite impulse response filter, IIR filter. This is the most general form. And what it says is that every time I want to compute an output, it's a sum of past values of the input, current and past values of the input, okay, plus, or in this case, minus sums of past values of the output. So it's recursive in the sense that the output of the filter, time in, is a function of past values of the output. Okay, so in general, the output feeds back into the filter. And here is a block diagram of this process. Okay, our first block diagram that we've seen, and here it is. Now, for my notes, or for the lecture, let me draw a line right to the middle of that. Okay, and to the left of this line, you will see everything only involves x of n. So here comes my input, x of n, and here's what the diagram means. I go into this little triangle thing with b naught. That means I'm multiplying x of n times b naught. I could have also drawn a little circle with the x like I did before, but either one's fine. So that the output is b naught x of n. I do this, I delay, there's that unit delay. I delay x by one sample, multiply that by b1, all the way down. And if you look at this, and you think about it for a minute, and down here you've delayed it 1 to m times, so you get x of n minus n times b sub m. And if you look at it, and then those are all added together, that's what this summation sign or sigma sign means, capital sigma. I'm going to take all of these guys, I'm going to add them all together, okay? And that, if you look at it, that corresponds to this part. That we sometimes call the feed feed forward section. Okay, that is our feed forward section of this filter. Why feed forward? Because we're taking this signal, we're delaying it, and we're feeding it forward. We're not feeding, well, I'll show you the feedback. But anyway, this is called the feed forward section. This, on the other hand, is called the feedback section. And what do we do with the feedback section? Well, basically, here comes our output. This is the output. This is y of n. That's going out, okay? But look what happens to it. In the same token, at the same hand, before it goes out, it gets fed back in the sense that here, this signal, y of n, the output gets delayed, so this is y of n minus 1. That gets multiplied by minus a1, and so on the way down, y of n, it gets delayed n times, capital N times, and it gets multiplied by its coefficient, and those two sum into this filter, which produce the output. And if you look at this section, that's this part. See? That's this part of the difference equation. So that's the feedback, that's the feed forward, and both of those sections, all the outputs from here, 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 they all get added together in this big summation block, okay? And the output of adding all those back, so the outputs at delayed times, they get added in, and the inputs get added in, and they all produce the output y of n. And that's what actually goes out. So that is a general form of this system with the difference equation. And let me just see something. Yeah, let me end the lecture now. About a couple of minutes left. I will just end the lecture by mentioning what I call here a Matlab moment. A Matlab moment. Just want to point something out to you real quick, and then we'll call it quits. Here's an example. N equals M equals 2. So I have basically 2 of the feed forward, these guys. So this sum has just 2 terms, and this sum has 2 terms. All right. So let's take a look. So in this case, y of n is equal to b naught times x of n plus b1 times x of n minus 1 plus, or actually minus a1 times y of n minus 1 minus a2 times y of n minus 2. So suppose that was my difference equation that I had, okay? What Matlab, it turns out Matlab, this is very nice, Matlab has a simple function called filter which does this for you. It's a very fast function, and it's very simple to use once you get used to the terminology. So what Matlab does is says, hey, look, oh, you know what, plus, I'm sorry, b2 times x of n minus 2 minus a1, yeah, there it is. So what Matlab does is to use this little spatial handy-dandy Matlab function. What Matlab wants you to do is define 2 vectors. I will call this vector equal b, and b will be equal to, and I'll have 3 components, b naught, b1, b2, okay? So this is an actual Matlab function. Once you know what the b's are, you can define this vector with 3 components. And the same thing with the a, in this case, because we're making a naught 1, that will be 1. Now for the a, now these are the feedback coefficients, you actually do put a minus a1, comma minus a2. So that is your a vector, okay? So Matlab defines 2 vectors, 1 of feed forward coefficients, 2 of feedback coefficients. And here I'm assuming that, I'm making that assumption that a naught is 1. In MATLAB, it doesn't have to be. A naught could be anything else. And now let's say, I've given you A1, A2, B naught, B1, B2, and I'm asking you, what would be the impulse response of this filter Well, in Matlab, and let's say I want an impulse response with 1,000 terms in it. You know, my impulse response will have 1,000 terms. In Matlab, what you would do is just what I said before, zeros of 1 comma 1,000. And then I will make x of 1 equals 1. And then I will do the magic. Let MATLAB do the rest. And here's how you would use MATLAB to do this. Filter B, comma A, comma X. So X is a vector with 1,000 samples. Y is also a vector with 1,000 samples. So that's the length of Y. And that will, since X we generate to be the delta function, input Y will be the impulse response output. So that is the filter function. If you want to read, and since it's perfectly general, I could have made N20 and M10 or whatever. All you have to do is define these coefficients for the filter that you want to examine. And by the way, MATLAB has more interesting functions too that are related to this. And if you want to find out more about it, so this is what MATLAB implements in general, you do help filter. If you haven't used the filter. A lot of people haven't used the filter functions. The neat thing about it is it's not even in the signal processing toolbox. It's just in the general toolbox. Well, that, my friends, is it. Again, I will make sure these notes are scanned, and we will continue from that point next time. One thing I want to point out is I probably will post a homework set before I go out of town. So be on the outlook for a homework set. And it'll be due, let's see, 21st is our first class. It'll probably be due in 2 weeks from then. In fact, I'm sure of it, okay? So that is it. I appreciate, and make sure you come back. We need more students, a lot more students. If we get, I think the number is 15, we get a TA. So tell your friends, friends. And I will see you then on May 28th. Okay, thanks.
That concludes this pre-taping of Electrical Engineering 483 with Professor Satorius on Wednesday, May 21st, 2014.